Okay, perfect. Recording started. So we are, the one thing I want to say, on Monday we will have 2-3 presentations by 2-3 of your colleagues, and they will be given at the start of the lecture after the questionnaire, but the questionnaire will take like 15 minutes. And then we will have 2-3 presentations, but we have 3 hours on Monday, and so we will have also the time to move forward with the general program. Now, this is our list of links. You may remember we discussed the model calibration and validation last time. So let's go there. And you also may remember that we discussed the least squares or sum of squares objective function, which is this one. We also discussed the limitations, the advantages and limitations. Remember, we are talking about optimizing, parameterizing, calibrating a model. And in this specific case, it's a rain for runoff model, but this can be applied to any type of model of a system that you may use. And of course, we are talking here of automatic calibration. We discussed earlier trial and error and the visual assessment of model performances. Here we are talking about automatic calibration. And as I said, this is applicable, this objective function is applicable to any kind of system models that you can think of. And we discussed the advantages. The advantages is that it's a method, the least square objective function, that has been proved to be very efficient, has been proved to provide very good performances in terms of reliability of the parameterization. Because as I said, if we use different objective functions, which means different measures of model reliability, we obtain different values of parameters. And of course, not all of them are equally performing. Some parameter set are better, as I said, for reproducing, for instance, the low values of the system variables we are trying to simulate. Other objective functions are more efficient in reproducing the high values. So we said the least squares, given that it squares the error, puts focus on the high values. So if we are interested in floods, in our specific case, the least square objective function is a good choice. On the other hand, we said if we are interested in modeling the low flows, droughts, if we are interested in water resources management, which is typically conditioned by low flows, then the least squares objective function is not the best choice. Now, there is an equivalent version of the least square objective function that provides then the same performances. We are expecting the same value of model parameters, which is derived from the least square objective function through a rescaling. Let me better explain the motivation. The least square objective functions, when you see the number, and you may remember we applied it to linear trend estimation, when you see the number in itself doesn't give any general indication on the goodness of the fit, doesn't give any general indication on whether or not the model is good, because it's typically a very large number. In fact, you may remember, and we will repeat it, that when we tried trend estimation, we took the square root of the least square objective function in order to compare the results between different trials. Why we took the square root? Because it's a smaller number, and therefore it is a bit easier to understand. It's easier to compare. So this is another, if we want, it's another limitation of the least squares objective function. It doesn't give this large number a general indication of model reliability. Actually, we would prefer to get a number that is easier to interpret, easier to be understood. Like, think of this example. If the objective function was varying between 0 and 1, with 0 meaning crap model and 1 meaning perfect model, would be much better, because we could more easily understand between 0 and 1 what is the performance of the model. So the idea was try to elaborate this least square objective function, try to rescale it in a range like 0, 1. You will see that the obtained range that we obtained through rescaling is not precisely 0, 1, but the idea is to elaborate an index that it's easier to be interpreted. And therefore, some people had the idea of rescaling the objective function. So how can we rescale it? In 1968, Nash and Sutcliffe proposed a rescaling of the least squares, which you can see here. And this is called the Nash-Sutcliffe efficiency. By the way, the 1968 paper by Nash and Sutcliffe, it's still the most cited paper in hydrology, in the history of hydrology. So it is a very trivial derivation, as you will see, that allowed them to get to be the most cited scientists in hydrology. So the rescaling is obtained by taking the least square objective function, which you see here in the right hand side at the numerator of the fraction of the numerator of the fraction, which I am indicated now with my mouse here, is precisely least squares. Okay. Now, at the denominator, what you see is the least square objective function that we obtain if we replace the model prediction x hat t. You see the model prediction at the numerator is indicated with x hat. At the denominator, the model prediction, model simulation, it's replaced with the average of the true values, x bar. So what is the meaning of doing that? The meaning is to compare the least square objective function of the model with the least square objective function of the so-called trivial model. The average of a variable is assumed to be the trivial prediction. What prediction would you make for any variable that you may consider if you are given no models, no information at all, but you are given only a set of observations? Of course, if you don't have any additional information, your trivial, naive prediction would be the average. Okay, so if somebody asked me, what is your prediction for the mean flow value of the Po River next year? Okay, and I am given no information. The only information is the time series of the Po River that you have, because we used it for some exercises. I would compute the mean flow of this time series, and I would say, okay, the average flow for the next year is, and I would give the mean flow. Because this is a naive prediction, a naive model. In fact, the average or mean in statistics is called the expected value, precisely because it's a naive prediction. It's what you expect if you don't have any additional information. So the idea here is, at the right-hand side, to compute the ratio between the errors that you make with your model and the errors that you make with the trivial model. So you understand that if the errors in terms of sum of squares that you make, it's larger than the trivial model, then your model is really useless. And if the error that you get with your model is comparable to the error given by the trivial model, then your model is useless still. If the errors that you make with the model are less than the errors that you make with the trivial prediction, your model is useful to some extent with respect to the trivial prediction. And of course, if the errors of your model are zero, are identically zero, your model is perfect. Okay, and then you get here the numerator that is zero. At the denominator, you have something different from zero because it's the error from the trivial prediction. So basically, this second term at the right-hand side varies between zero and something that is not upper bounded, because the error that we can make with a model is not upper bounded. It may happen that your model is worse than the trivial prediction. So your model is, as I said, very useless. It's better to use the trivial prediction. It's better to use the average. So the second term at the right-hand side, once again, is varying between 0 and plus infinity. But of course, what we would like and what we aim to is 0, is getting 0 errors in the simulation. So the idea is, at the right-hand side, to compute 1 minus the ratio, the fraction that I just described. So if the model is perfect, the Nash efficiency results in 1. If the Nash efficiency results in 0, it means that the error that you make with your model is similar to the error that you make with the trivial prediction. So the model is useless. But there is no lower limit for the Nash efficiency. It can be lower than 0, it can be negative, which means that really your model is to be rejected. So you see the advantage that you get with the subjective function. It is all in all similar to the least squares. It gives the same results. But on the other hand, it is bounded typically in the range 0, 1, even if it is not formally bounded, because it may result in an error that is in a value that is lower than 0. But typically, given that typically we test models that are better than the average value, are better than the naive model, typically we get values of the Nash efficiency in the interval 0, 1. I give you an indication in hydrology, which is very, very general. So you have to take it as a rule of thumb, okay? Usually we say that a model with an Nash efficiency less than 0.5, it is not trustable. We aim to models that get a Nash efficiency that is larger than 0.7. It is quite rare that you get efficiency larger than 0.9. So typically you get efficiencies between 0.7, 0.9. And, you know, take these indications as a pure rule of thumb, okay? Because it depends on the model, it depends on what you are simulating. There are variables that are easier to simulate. Typically the variables that you aggregate over long time steps, like monthly values, annual values, these are easier. And there are variables, typically those that are simulated at fine time step, daily, hourly, that are more difficult to reproduce. And also, you know, precipitation is more difficult to reproduce than river flow, for instance. So, as I said, it's a pure rule of thumb. But it is true that from a technical point of view, if you get efficiencies lower than 0.5, it is not very useful. The Nash efficiency is very similar, but not precisely the same value, to the R-square coefficient, which you may have heard of. If you never heard of it, don't worry. We are not considering it here, okay? And they are more or less similar. Perfect. There is one thing that I wanna, one consideration that I wanna make. Keep in mind that these objective functions are minimized typically, or let's say optimized, because the Nash efficiency is maximized, not minimized. I aim at the value of 1. The closer I get to 1, the better is the model. So it is maximized, not minimized. So typically these objective functions are, let's say, the word optimized Optimize include both minimize and maximize. Be aware of these differences, minimization, maximization, and if something is not clear to you, ask questions, okay? So least squares is to be minimized, and less efficiency is to be maximized. When you use automatic procedures, for instance in R, these optimizations are done numerically, trial and error, numerical trial and error. And usually to these routines, you have to specify if you want minimization or maximization. Don't make mistakes because you understand that it's completely different, okay? If you minimize some squares, you get to target. If you maximize it, you aim to the worst model. So we don't have to make mistakes in that, okay? Now, as I said, these are optimized numerically. Okay, what does this mean? It means that when you run a calibration, optimization, parameterization, and you rerun it a second time, it may happen that the results are not the same. And this is it is perfectly fine because it's a numerical optimization. So when you use a routine, typically the routine starts with the initial values of the parameters, starts with a random search. The random search is different anytime that is performed. So don't be, of course, the results are similar. If you optimize the same model twice, the results are similar, but you don't have to look for complete identical value of results, okay? So when I said least squares leads to the same results as the net efficiency, you don't have to take it literally, okay? So in R, if you minimize least squares and you maximize net efficiency, you get very similar values of the parameters, but not precisely the same value. Of course, there is a numerical routine in between that is used, okay? So these, these sensibilities, this understanding of how things work, it's essential for you if you want to avoid to get puzzled when you make applications. So now you may, in a way, forget about it because when we make exercises, basically they are not evaluated, and at the exam you are not asked to make any exercise. So you may also forget about it, don't care about these details. But within a few months, within 1, 2 years, 3 years, you will be working professionally. And it's extremely important that when you're working professionally, you gain these sensibilities. And for this reason, I'm telling you, try to hurry up in understanding, learning, getting sensibilities. Okay. Now, sorry. Now let's move forward with another objective function. We will consider a couple of them, okay? A couple more. Remember, please, these objective functions are very easy to be remembered, so make an effort because at the exam they may be asked these relationships. It is not difficult to remember them, they are very simple, okay? Now, I already mentioned the possibility to minimize the sum of the absolute error, okay? It is perfectly fine. In particular, if you are interested in getting more precision in the simulation of low flows, the sum of the absolute errors is a viable opportunity. And it is very simple, as you see the formulation here. And in case you want to put even more emphasis on low flows, You can also use as objective function the sum, is the second equation, look at my mouse, the sum of the relative errors. It is sum of the absolute relative errors. Okay, it is written here. It is like the summation of the absolute percentage errors. It's not really a percentage because it's you get any error and divide the error by the corresponding observation. So in order to get a percentage, you should multiply for 100, which is not the case here. So we call it sum of the absolute relative errors. And this puts a lot of emphasis on the low flows, on the low values. And because clearly you understand that if you have small error and you divide it by a large observation, the small error becomes really small. If you get a small error and you divide it by a very small observation, you magnify the small error. And therefore, by summing the relative errors, of course, you put emphasis on the low values. What is the problem here? The problem here is that if observations are tending to zero, then the absolute relative error tends to infinity. So, of course, if you have zeros in your xt, in your observations, you get an error because dividing by zero, of course, gives an error. But you may not get errors, so you may be fine with the result. But if there are observations that are very close to zero, then you give really a lot of weight to the errors in simulating these observations. So this is to be used carefully. If you have variables that are quite far from zero, it may give good results. If you have intermittent river flows, for instance, you can't use this because you have zeros. But even if you have very low values like 0.0001, then you have to be very careful in using it. And usually what we do is to look carefully at the problem from a technical point of view, to look at what we are interested in. So if we are interested in the simulation of the low flows, then we have to we may use the sum of the relative errors. Otherwise, if there are zeros, we can't use it, and then we use other solutions. I would stop here. Keep in mind that there are tons of objective functions that may be used. There are some objective functions that look specifically at the timing, for instance, of the peak flow. And therefore, they don't look really at the error in the observations, but they look specifically at the timing. There are objective functions that look at the volume, simulated volume, for instance, of the hydrograph, and maximize the goodness of the fit of the volume of the hydrograph. So there are really tons of them, and we of course don't discuss any of them. There is one thing that I want to say that is not reported here. It is also possible to use multiple objective functions. It becomes a little bit complicated to find the best performing solution if you have more than one objective function. It is complicated because you understand the minimum of an objective function so the optimum of an objective function may be in correspondence of the worst value of the other objective function. So you have to find the combination that reaches the best compromise, which is not easy. There is a lot of theory behind it. And we don't discuss it because it is too specific. We are not interested in going into fine details. Just keep in mind that there is really a literature on that, a full literature. And you may also decide to use, for instance, both least squares and sum of the relative error and find the solution that absolute relative error, sorry. And you may find the solution that reaches the best compromise between the two. And as I said, there are there is a full literature. There are R programs allowing you to explore the use of 2, 3, 4, 5 objective function. You can really get a lot of fun in model optimization and parameterization. Okay. Now let's move forward with another type of calibration that we may use. It is the calibration through expert knowledge. Okay. So far, what we discussed is calibration through optimization of model performances in the simulation of observed data. Fine. And so we discussed trial and error by looking again at the simulation of observed data, and we discussed automatic calibration through objective function. But what if you don't have any data? It may happen that you have to calibrate a model, you have to make a prediction of future climate, make a prediction of future river flows, future rainfall, without any observation, without any information on the process. So how can we move forward in such a situation? Of course, this is an interesting problem. It's a problem that is discussed once again by a full literature. For instance, in hydrology, there are books, entire books dedicated to prediction in ungauged basins or ungauged catchments, which deal with this interesting problem. And what we do usually is to use the so-called expert knowledge, which means calibrating, finding the best value for model parameters, calibrating the model by using our understanding of the process, our understanding of the model, and guessing the value of the parameters. And there are several values, several techniques for doing that, because of course, expert knowledge is not a real guess. You try to make use of alternative information, alternative with respect to the data. There are several ways of doing that, which we don't discuss. But I want to tell you that very often, calibration of climate models is done through expert knowledge. Why? Because climate models are not conceived for reproducing the weather. They are conceived to reproduce the climate. Their purpose is not to reproduce what will happen in Bologna on a certain day. They are purposed to reproduce the climate, and climate, you know, that is statistics of the weather over long time periods. And therefore, very often you don't have these statistics available for in terms of observed statistics of observed data. You don't have them available because very often the observed data are lacking in terms of like, for instance, rainfall, temperature, rainfall for a given location, they are lacking, or they are available only for short durations. For instance, if we consider Italy, the whole of Italy, we have distributed rainfall over Italy, but only for the past 50 years. Now they are becoming available for the past 70 years. They are not really observed data, but in a way, they are derived from observed data through a kind of reanalysis. But, you know, even 70 years, it's not a long time in order to calibrate a climate model that has a lot of parameters. So very often the climate models are calibrated through expert knowledge. Of course, if you calibrate through expert knowledge, you get an uncertainty that is larger. You can understand that. If you calibrate with observed data, you have a term of comparison, which is a real observation. And it's a number that was measured. It's less uncertain. There is some uncertainty in measurements, but they are less uncertain with respect to your perception. which is subjective, and therefore it's more uncertain. So there is more uncertainty. And also it is difficult to quantify this uncertainty, because you understand that if you simulate observed data, you get errors, simulation errors, and these errors give to you an indication of the uncertainty. It's an indication of the error that you may expect when the model is used in prediction. If you don't have observed data, you don't get any simulation error, any indication. So it's difficult to assess uncertainty. And then you have to take into account that climate models very often are not tested. And this is something that you should try to understand. Like, if you are using a climate model to get prediction of future climate in your future profession, try to understand if the model was tested, if there is a kind of uncertainty assessment. I tell you, it's not easy. It's not easy to understand how climate models work. It is much easier to understand how an hydrological model works. Usually, when you see an application of the linear reservoir, of the rational formula, usually this application is corroborated by, is supported by uncertainty assessment and indication of the error that you may expect. When you deal with the climate models, it's much more difficult that you get this information. The reason is very simple, is that while hydrological models are largely used in engineering, I mean, the linear reservoir is largely used for engineering design, and it has been used for tens of years. Climate models are still not yet used for engineering design, and therefore uncertainty assessment is an optional, while in engineering design uncertainty assessment is a must. So this is why when you look at models that are still in the domain of research and not in the domain of the technical applications, it's unlikely that you find an indication of uncertainty, an uncertainty assessment, if the models are still in the research domain. For models that are already in the domain of technical applications, it's very likely that you find indications allowing you to make an uncertainty assessment. But the calibration through expert knowledge is important. And as I said, we don't go into the details. There are instruments, techniques that may help you if you don't have data. Okay, let me have a look at the chat. Do you have any question? Let me see. I don't see any question on the chat. Okay, so if you don't have any question, I anticipate that I want to introduce the next topic, and then I will save some time for exploring a little bit more the exercise that we made last Monday, we introduced last Monday. So, what is model validation? Model validation. First, let me make a premise. Usually when I ask this question at the exam, what's the difference between calibration and validation? I don't know why, but I think it is very easy to explain what is the difference, but the students usually fail in this question. And it's a question that you can find also in the quiz. So try to pay some attention to this, because sometimes it happens that when things look easy, we pay less attention. And actually, you know, if you make a mistake in a question, in a difficult question at the exam, the mistake can be in a way forgiven. But if you make a mistake in a very easy question, it is an embarrassing situation. So my suggestion is try also to pay attention, especially if I tell you, to the topic that even if they look easy, they may be the subject of a question at the exam. First suggestion, okay? And second suggestion, I don't know why, but I think there are sometimes convincements among the students that some of the things are not asked by the professor at the exam, and I don't know why, but it is, I can really perceive that. Maybe because in 1 year I don't ask the question at the exam, and then there is of course a passaparola, as we say in Italian, so the word passes from mouth to mouth, and maybe the students get convinced that that kind of question will not be asked. And I think it is much better if you explicitly ask me, and if you are in doubt, if you think that something is not the subject for exam questions, I mean, you can freely ask. There is no problem. Of course, it is likely that I say yes to, but in some of the cases, indeed, I say no. You have seen that for some of the topics that we discuss, I don't have any problem in saying that I'm not asking any question on them at the exam. But if you are in doubt, ask me. Okay, it's not really a problem. So validation is something that I often ask. So what is the difference between calibration and validation? I think the wording may already suggest to you the difference. Calibration is looking for the best set of model parameters. Validation is to verify this set that I found. So basically, I calibrate a model, but then I want to test it. I want to test the result of the calibration. And this is perfectly fine. I mean, before applying a model, especially if you are responsible for the results in some way, it is perfectly fine. It is highly advisable that you make a testing, okay? It's like when you prepare a car, you know, or when you prepare any kind of system, and usually, even if it was designed according to the perfect theory, even if everything went well in the construction, etc., when you get the prototype, what's called the prototype, you want to test the prototype by typically making a stress test. So you try to test it in the worst condition that you may experience. This is perfectly fine. It's done in several practical design exercises. Even with bridges, you know, when you design a bridge, everything goes fine. You build the bridge, everything is fine. But then you make a test, a stress test of the bridge. You put a long line of trucks with full load over the bridge in order to see what happens. Okay. So how can we perform this validation? Okay, so in calibration, in parameterization, you use a set of data to train the model, okay? Model training is another synonym for calibrating, optimizing, parameterizing. In some disciplines, in hydrology, it's not frequently used. In some disciplines, especially in machine learning, it is used the term training. I think it is meaningful because it gives the idea that you use the data to train the model. Okay, so you use the information content of the data to provide to the model the information that the model needs. As a result, the model is trained against the data that you used. And we often say that we want the calibration data set be large. I said, the longer the data set that you use for calibrating the model, the better it is. Because if the data set is large, it's extended in time, extended in space, whatever, a large data set, the result is that you get the model trained with respect to a comprehensive set of situations. You understand, if you calibrate the model only with respect to 1 week of river flows, then you are not as relaxed as you calibrated the model with 100 years of river flows. It's clear, okay? Now, in any case, the result is that the model is trained with respect to that specific data set. When you go to application, the model is run in a different situation. it's not the same situation that was used in calibration. It's a different situation. So what you expect is that the model is not trained for that different situation. The model has been trained on a set as large as possible of known situations. When you go to application, it's a different one. So the model is not trained. Of course, you expect that the new situation is to some extent similar to those that you used to train the model. So you expect that the performances will be similar, but strictly speaking and in general, you expect more uncertainty because the model is not trained. Okay. As a result, validation aims to test the model in a situation that is similar to the application, so aims to test the model with respect to a situation that was not used for model training. And for this reason, it is also called out-of-sample application. So you may read the sentence, model validation has been performed with an out-of-sample application. What does it mean, out-of-sample? It means out of the data that were used to train the model. Okay, so we perform validation, once again, by running the model with respect to a situation that has not been used for training the model. So we use to run the model observed data that were not used to calibrate the model. Okay. I hope it's clear the concept. Now, to make it possibly clearer, let me make an example and let me select the sentence that I want to read now. A simple and obvious way of performing validation for hydrological model, but whatever model I would say, is to use the so-called split sample procedure. Okay, let's move forward. The observed data are divided into two groups. One group is used for calibration, and the other group is used to test the model. So the model is tested with respect to data that were not used in calibration, the data from the other group. Okay. Now, in this way, we emulate a real-world application. Okay. So we perform an out-of-sample application. Perfect. So you have a set of observed data. You split the observed data into groups. One group is used for calibration. The other group is used for validation. It is a straightforward procedure. It is what we obviously would like to do. Of course, there is a clear limitation here. Usually we work with few data only. And therefore, you know, it is a pity that we split the data into groups. And it's a pity that we use only a subset of data to perform a model calibration. Still, if we want to use validation, this is an obvious procedure. Then the procedure may be repeated by inverting the group of data used for calibration and validation, therefore obtaining two validation tests. If the sample is sufficiently large, it can be split in three pieces, and so forth. Of course, if you perform different calibrations, you obtain different values for the parameters. Okay? Because I already said that even if you use the same data set, any calibration, any numerical exercise leads to different results. In this case, you are using for calibration different data sets, and therefore you may also obtain very different results. So then there is the final question, what is the final value? of the calibrated parameters. And depending on the application and depending on your creativity, you have to find a solution. An obvious solution may be, okay, I performed 3 calibrations, I got 3 parameter set, let's take the average. The average, you know, may be a good solution, maybe not. It depends on how many parameters you have in the model, and you have to test it. So if you take the average, let's perform another validation, okay, in order to test it, if it was good. Another solution is, which is probably more recommendable, once that you finished your validation and you are happy with it, and validation that has been performed perhaps on 3 different groups of data, let's suppose that you are fairly happy, okay, with it. Then a possible solution is to repeat the calibration by using the entire data set, so that at the end of the story you get a final value of the parameters that has been optimized over the whole data set. This is reasonable. Of course, this final value is not validated, cannot be validated, because you don't have, you used all the data, you don't have data left for validation. On the other hand, you performed validations by using subsets and the validation were fine. So, I mean, you may be allowed to say that even the new data set, the new parameter set must be reliable because the model passed several tests, okay? You understand that when you turn to application, you may experience very different situations, like I performed 3 validations, 2 of them are fine, and the third one is a crap. So how to do, what to do? And so in this case is, as I said, your creativity, your sensibility, your experience. And your experience doesn't mean that you are an old person. It means just that you perform a very informed assessment, and you make, you select, you move forward with the most advisable solution, the most reasonable solution. Okay, as I said, when you turn to technical applications in the presence of uncertainty, you have to be very careful and assess the peculiarities of each situation that you may experience by using a lot of care. Okay, if you're interested in these topics, try to look at this link, cross-validation, which gives to you an idea of the amount of study and research that is being dedicated to these topics. And of course, we cannot also for this topic to go to look at the details because it would take too long. But it is important that you get an idea. You get an idea of what are the informations that you may need if you get in your profession or in your in a profession in general, maybe also research your profession. What is the information that you need if you want to move forward, if you are required to move forward, okay? So, of course, you cannot explore all of these links that I'm providing to you, but try to make some for the topics that look more interesting to you, try to make some refinement. This is also why I suggest you to make presentations, because you have to get trained like a model in with respect to several different situations that you may experience in your profession. Remember, passing the exam is not a target, or I mean, is a temporary target, but your real target must be to get ready for your profession, because this is the key indeed to get to target. Okay. Any question? Let me look at the chat. Okay, no questions. Now, if I go back to the list of the links, the next link is decision theory, and it is a topical issue in climate change, which we will start discussing on Monday. And it will take to us a couple of weeks because we have a couple of weeks to get to the end of our course. And it is a topical issue because we also have really a final link, which is real design of climate change adaptation actions. Decision theory, as I said, is a topical issue because it is related to communication. So basically, when you have to take decisions by consulting stakeholders, then it is when you need decision theory. And so it is strictly related to communication. And so for this topic, for this reason, I think it is, communication in climate change issues is extremely important, as you know. And I think that the scientific community probably failed in communicating about climate change. And this is, in my opinion, the reason why the public doesn't trust very much climate predictions. And so we will start on Monday. Today, we have a little bit more than half an hour to go. I want to go back to our exercise because, as you may remember, the last exercise that we considered is this one, trend analysis for a time series of daily river flows. And here I notice now this "the" is not necessary. I would say that it's wrong in grammar. Okay, so I need to remember to change it. So we estimated the linear trend in the time series. And by minimizing the sum of the squared interpolation errors. Okay, I want to go back to this exercise and perform some additional experiments by using different objective functions, so we can understand how the results may change. In this case, I don't think they will change a lot because it is a situation where I don't think there is large uncertainty here. And also, I would like to discuss this by assuming that the errors are normally distributed and independent, something that we barely discussed, the meaning of normally distributed and independent, compute the standard deviation of the interpolation error. Okay, let's then go back to the suggested R code. Okay, suggested R code. Now, I want to open it in RStudio. Let me see. RStudio is here, and let me close a couple of windows which we don't need. Okay, and let's copy the R code here. So the R code that I found in the website was downloaded. Okay, and it's downloaded here. Just 1 second. I'll show it to you. It's downloaded here, and this is similar to Notepad. So if you downloaded it, the R code, if it is not directly opened in RStudio, you may open it in Notepad. And then I am transferring it into R. So let me go to RStudio and let me open. I need to set the working directory where I downloaded the file. to source file location. Perfect. And then I just need to open file, and this is what I downloaded. Just 1 second. It's called has trend river flow. It is this one, open. And why it's not opened here? 1 second. Let me open again. Let me open it again. Here it is, somewhere here. Okay, let me see if it is open this time. Okay, it doesn't find it. I don't understand. Let's see. Okay, let me try to open again. As trend. 1 second. Okay, I got it. Okay. Now I need to get the file of the synthetic river flow, and let me try to scan the data like I did last time. Okay, you see that we read the 20,000 items, and then I can make the plot. I am working now by selecting over the source window and clicking on run. Okay, and here we get the plot like we did last time. And then let me try to optimize with the objective function. You may remember that we did it with the objective function sum of squares. Let me create this function to be optimized. We did it already last time. Okay, and then I can use the optimize function, but before than that I need to set the intercept. Okay, and then I can use the optimize function. This is what we did last time, and now we can see the results. Okay, so we got for slope 0.007, and as objective function sum of squares we got this number here. Okay, and now let's remember that this is the square root of the sum of squares. Okay, now let's suppose that we want to use the sum of the relative errors, not the sum of squares. How can we, or let's say sum of the absolute errors. Okay, let's see how we can make it. So what we have to do is to change the function SumSQ. Now I want to show you the function. It is this one, the function to compute the square root of sum of squares. It's this function, okay, and which I uploaded into R and I minimized. And remember, I minimized it with the optimize function of R, okay, which optimizes in this case only the slope, and I optimize the slope after fixing the intercept. Can you follow me? Everything is clear? Let me look at the chat, because basically so far I repeated what we did together. Basically so far what I did is to download the R code and execute it. So you can also select everything and then run the whole of the R code and you get the same thing. You see in the R console, I got again the optimize function, and if I want to look at the results, you see the slope is 0.07. Of course, this slope depends on the intercept that I fixed, which is an arbitrary selection of the intercept, but let's assume that it's fine, okay? Okay, good. Now, if I want to make the computation of both intercept and slope, before changing the objective function, let me make the computation of both intercept and slope. We discussed last time, and we did already, the computation, calibration of both intercept and slope with the LSFit function of R. Let's remake it again. And if you make it again, I just selected the LSFit function, and I selected also the visualization of the results, and I pressed on run, okay? And you see that we get an intercept that is 1515, and the slope is 0.56. So let me now fix the intercept. And let me see, how did I call the intercept? A, I think. Okay, A equal, let's fix A at this value here. Okay, copy and paste. In this way, I am fixing the value of the intercept at its precise value, optimized through a straight line estimation. Now, if I repeat the optimize function now, I should get a value of the slope, we did it already last time, that is comparable, that is 0.56. Let's see, comparable to what we obtained previously. You see, this is the correct value of the slope of the trend line, and it's the correct value with the correct intercept. Now let's change the objective function. Okay, so the objective function is here. If we want to repeat the estimation with a different objective function, we have here, we can here remove the square root, and then you only get the sum of the absolute errors. Okay, let me run it into R, and let's use the optimize function again. Now we are using the sum of the absolute errors. I cleared the console. Let's run it. So you see that now the result changed quite significantly. Before than that, we had a positive slope of 0.056. Now we have a negative slope of minus 0.01. It's a different story, a different result. And what if we wanted to use the sum of the relative error? What we have to do is here compute the sum of the absolute difference, and in this case, let me just, I think we can just divide by river flow. Okay, and here, let me see, the parentheses here, yeah, it's before the summation. Yes, I think we should, okay. This is the sum of the relative errors. Run, so I'm, sorry, there is something wrong here. Let me see. Okay, so 1 second. I think I need to displace the parentheses. Yeah, in a different manner. Let me see if I do like this. Okay, let me see. Run. Now it worked. I think it should work in this way. Let's see the estimation. You may want to make a check, which we don't make here, because it doesn't give any error, but I'm not really sure. I'm sorry. Let me clear. Don't understand what happened. Okay, perfect. So this is the result, and you see that now. Let me repeat it. Sorry, because I want to make sure that I did everything correctly. Okay, run. Yeah. Okay, now the slope is again negative. It's minus 0.03. So you see that different objective functions give different results. Now, this fact, it's inducing some considerations like what is the reason why I get these different results? The reason may be that, for instance, there is a lot of uncertainty here. This is my guess. This is my guess because actually the results are different but are not markedly different. So the fact that I pass from a positive slope 0.05 to a negative slope 0.03, actually the difference is not very large and may be due just to the presence of uncertainty. Now, how can I check the uncertainty of the estimation? This is the item that I wanted to discuss with you. Okay. Now, when you apply the least squares procedure, which is theoretically, as I said, demonstrated to be efficient, to be a good procedure, you can use the underlying theory to estimate uncertainty. And we don't go into the details of the underlying theory. I just want to tell you that the fact that we can say that least squares is a good procedure, it's because it was studied the theory underlying it. And it was analyzed through this theory, the uncertainty. And it was proved that the uncertainty is anyway acceptable. And so at the end of the story, the same theory allows us to derive an estimate of the uncertainty. Basically, what the theory does is to look at the errors. So when you fit a straight line to the data, you get errors, differences between the observation and the straight line. And by looking at the errors, the theory estimates uncertainty. And uncertainty is estimated in a very convenient way because the procedures for straight line estimation give us already a range of uncertainty for the slope and the intercept. So the procedures give us already an estimate of uncertainty that is ready to use. So basically, besides the optimum value of the slope, least squares gives us a range of the slope to evaluate uncertainty. This is what I wanted to discuss with you, to give you an idea that these procedures that are, boring because, they involve the use of statistics, the use of some math, but these procedures at the end of the story and the theory, the boring theory underlying these procedures are very useful in practice. How can we get this range, uncertainty range for the slope. Let me clear the console. You may remember that we used the lsfit function here, okay? And this is still there. It refers to least squares, and the result of lsfit was placed into a list. Into a list is, as I said, a group of information, a list that contains several information, and one of these information is the coefficient. So if I call the subset of the list called coef, I get intercept and slope. But there is another subset of the list which gives to me the range for the slope, and it's PR2 dollar. I think it is something like standard. Let me see. Okay, let me see the content of the list. Names PR2. Sorry for that. Let me. I typed in the wrong windows. Sorry. PR2 ST. Coefficient residuals, intercept QR. I think I need to compute another step. Let me write this. PR3 is equal to LS diag PR2. Sorry. Let me repeat once again because I don't remember the name of the function. I have to, okay, it's ls diag, okay, PR2. Let me, okay, perfect. So what I did here is to compute the diagnostic of the least square estimation, of the straight line estimation. Now, let me see the names of the obtained list. STD dev, this is what I look for, PR3. This is also reported in the example of the code here. I think, no, it's not reported, sorry. 1 second. I don't understand this error, so this warning, let me see, PR3. Okay, here it is. I don't understand this warning, but let's ignore it for now. This is the standard error of the slope, and the standard error is 0.001. So the standard error means that if you want to get the range of the estimated slope, you have to compute the estimated slope plus minus the standard error. So let's make it. Let me clear the console. So PR2 coef 2 should give the slope. Perfect. Perfect. And then we can make PR2 coef 2 minus PR3 standard error 2. And this should give to me the lower value. No, let me see. Let me clear again. Okay, let me repeat the computation of ls diag, because I don't understand why I get the continuous this warning. Okay, and let me see here now, standard error to, okay, this is the lower value and this is the upper value. So as you see, this is this is the range of the estimated slope. So how did I compute it? Let me just make a summary, because meanwhile I got the warning that made the computation a little bit complicated. So remember, let me make a summary, okay? So remember that we estimate the straight line by using this function lsfit, and remember that I can I can see the results by displaying the coefficients. Perfect. Now, this is the estimation. In order to compute the uncertainty, I need to compute the diagnostic of the estimation, which is this one. And then in the diagnostic of the estimation, I have the standard error of the slope. And therefore, I can compute here the lower value of the slope and here the upper value. So in this way, you can get an estimate of uncertainty. And of course, we used here the least square function, which is embedded in the function lsfit. If you want to make the same experiment, uncertainty estimation, by using the another objective function, for instance, sum of the absolute errors, you have no theory, no underlying theory to support you in the uncertainty assessment. And therefore, you have to compute uncertainty in a different way. You cannot use a pre-written R function. You have to analyze the errors with techniques that we don't discuss here. Okay, but in case you use the least squares, and in R you have already everything that you need in order to estimate uncertainty. Another remark, these theories, least squares estimation, are based on assumptions. And here, if you look on my website, let me, inductive and deductive estimation of climate change and climate impact. It is where we discussed the trend estimation. So if you look in my website, there is a consideration, a discussion of this. Computation of the confidence interval, which is what I just did. I didn't discuss the significant level of the confidence bands given by R. I'm not interested to discuss it here because it would make my treatment even more complicated. I think it's already very technical, so I don't want to get into details. So let's just focus on the concept. Computation of the confidence interval is affected by assumptions, and this is what I just said. These assumptions are done on the simulation error, and in particular, the assumptions are related to its probability distribution. So there are assumptions on the probability distribution of the error, and in detail, the residuals are assumed to follow a normal distribution, the residuals, the errors, and to be uncorrelated. Okay, this is why in the test of the exercise, we found this. Let me open the text. By assuming that the errors are normally distributed and independent, independent is a synonym of uncorrelated, compute the standard deviation of the interpolation error. This is what we just did. with the function ls.diag and the operations that I did into R. Okay. Now, I understand that it may look complicated to follow it online, and you know, in order to get clear the situation, you should repeat this by yourself. It is very easy. You have the video, so you may repeat it for sure. Now, as you know, this is not something for the exam, even if it may happen that at the exam we discuss what is a confidence interval for a given significant level. And we can discuss at the exam this because we already discussed in another lecture what is the confidence level. And so pay attention to what's written here. But of course, you don't need to make the computation for the exam. What we did today, like everything we did for the exercises, you don't need at the exam to prove that you have skills in doing that. I'm just providing to you the information because, as I said, I think that you need in a way to get prepared also on technical applications. So this is another seed that I give to you, and a seed for possible training with respect to situations that you will not get at the exam, but you for sure will get when you are in the profession, whatever you do, because you are technicians, you are studying science, so whatever you do in the future, you will have models to apply, and in any kind of a specific field. And therefore, I think it is interesting to get trained with respect to uncertainty estimation and whatever. We have a few minutes only. I want to anticipate the next exercise because it's more specific. It's an application of the linear reservoir range for an off model. And I just want to suggest to you to look at the text, okay, and to look at the data set that we have, which is available on the website. The link's here, but it's also available here. You see, if you click here, you get this data set, and this is the second one. And you have an R code here, which is here. It's already in opened in the RStudio, so please get 5 minutes to have a look at the next one. You don't need to start it, but you may also try because you have the R code. So in this way, you can follow me better when we will make this exercise, which is the last but one, because we will have also a final one on decision theory. Okay, we are almost there. So any question, any critical comment? Remember that on Monday you will have the anonymous survey, and therefore you will have the opportunity to make any critical comment you may wish. Any comment? Any question? Okay, very good. Thank you very much. Have a nice weekend, and see you Monday morning in physical presence, room TA10 as usual. Ciao, everybody.